So we're just a small part of the team at Sony Interactive Entertainment that's been contributing towards sample-based PGO, sometimes alternatively known as FDO, or feedback-directed optimization. So this is essentially a story or a case study about how we integrated an existing LLVM feature into the PS4 SDK to the benefit of our users, and the changes that we contributed back in the process, and what we learned in our analysis, hopefully to the benefit of the entire community. So let's start with some background. So games are essentially firm, real-time systems that have to crunch a lot of numbers in a very small amount of time repeatedly. If a game doesn't keep a solid frame rate, then the players notice. So we wanted to do everything in our power as tools providers to help game developers hit their frame time budgets. So a consequence of this is that typically all debugging happens on fully optimized builds. Turning off optimization will usually make the game run too slowly to be playable, vital to reproducing issues found in testing. So game developers also often have quite aggressive development milestones to hit. So it can be hard to convince them to try new toolchain features if the barrier to entry is too high. So we've previously had success introducing LLVM's link time optimization to the PS4 SDK, and we figured the natural next step was to look at LLVM's profile-guided optimization. So there are two primary methods for collecting data for a profile guide file: instrumented and sampled. The instrumented approach relies on creating a new build configuration where the compiler adds code to the generated code to track how often different parts are executed. This code can either be added in Clang or later on directly to the IR in LLVM itself. And the IR instrumentation is generally able to be a little bit smarter about where to add counters, so it's less intrusive when collecting a profile. So for this reason, we're only supporting the IR approach on PS4, as the runtime intrusion when profiling is vitally important for the aforementioned reason. You typically need to actually play the game for some amount of time to collect good representative profile data. So reading the paper here presented by Google engineers at CGO last year, we were strongly intrigued by the possibility of the completely separate sample-based PGO approach. So this is where you use an external profiling tool to collect data about the runtime characteristics of your program at the machine instruction level, and then map that back to the original source code using the debug line table info. The claim is that this technology led to an 8x increase in the number of users enabling PGO compared to when only the instrumented approach was available. And all of our work here is entirely based upon the foundations laid by them previously. So our hypothesis was that the runtime intrusion and the overall workflow of the sampling approach would be better than with the instrumented approach, but we still had an open question on the quality of the resulting data for the profile guide file, and therefore the overall runtime improvement to be expected from sample-based PGO. So this is kind of a high-level overview of the instrumented approach. We have our two different build configurations, each with different PGO-related command line switches, one to generate the instrumented executable, and the other to use the profile guide file to actually create the final optimized executable. There's an intermediate step using the LLVM prof data tool to convert the raw outputted profile data to an indexed format for consumption by the compiler. In the case of games, we can't rely on the usual behavior of the profile data being automatically written to a file on the process exit, because games never actually exit. Instead, they're forcibly quit by the OS when the user chooses to exit the game. So game developers would need to add an explicit call to a runtime function to write the raw profile file, which they'd hide behind a debug menu or similar. So here's a trivial contrived example just to show what I mean by profile-guided optimization. This is the instrumented approach. In this case, we execute function foo 1 billion times, or function func. And 1 in every 100 times, the error condition will be encountered, so we early exit, and the blue line will run. And in the remaining cases, the purple line will run instead. Without a profile guide file, the compiler doesn't know that the purple code is hotter, and so it's placed at the end of the function with an additional jump over the colder blue code. Adding compiler instrumentation results in additional instructions to increment counters on entry to the basic blocks. In this case, it's removed the tail call optimization and made purple a common successor block to both red and blue, putting counters in blue and purple. And if we execute the program and look at the counters, then we can see that the purple counter shows 1 billion exactly, and the blue counter exactly 1% of that. So we can infer that the red block also has 1 billion hits without an explicit counter being necessary. When we then remove the flag to create the instrumentation data, and we replace it with the flag to use it instead, and apply that data, it results in more optimal basic block placement, where the hot BBs are clustered together with the jump only taken for the colder error case. So for the sample-based approach, our aim was to only have a single build configuration, and from this configuration, new profiles are collected and old profiles are applied. So this is also the build from which all debugging will likely be carried out. So it's vitally important we don't do anything to make the debugging experience worse here. So this rules out any sort of mode that would optimize debug data toward producing accurate profiles at the expense of debugging, or vice versa. So taking the same example, we build it with debug data. This associates the line numbers with each instruction, and in this case, red is line 5, blue line 6, purple line 9, which is the closing brace. And we build it with debug data, run it through the profiling tool, samples are then captured at the machine instruction level, and the debug line table is used to associate these samples back to source locations. The first line of the function, red, has just over 1 million hits, with purple having a similar number, and blue, as expected, has about 1% of the hits of either red or purple. So we don't have perfect, precise numbers like we did with the instrumented case, where we had exactly 1 billion executions, but the important part is the ratio between red, blue, and purple, which is almost exactly right. So building with that profile file, again, the compiler is reordered to put the common case first, as we'd hope. So there's nothing new here. This is all stuff that already existed in the compiler before we came along and started looking at it. There is really cool ongoing work happening in the community by other engineers in the LLVM community to further improve it, though. So typically, for the sample-based approach, you'd use a tool like Perf on Linux, but we wanted to design our own workflow using our own existing profiling tools for PS4, so we came up with the following user-facing workflow. So it's hosted inside one of our profiling tools, Razer CPU Live. So let's assume we're running a game on the development kit already. We just click a button to start a profiling session, and this starts capturing data using a custom low-intrusion trace that we developed specifically for the PS4 hardware. And then we play our game for some amount of time, whether that's a few minutes or a few hours. And once we're done, we stop our session and click the button to create a PGO file. And then underneath, invisibly to the user, this invokes a version of the AutoFDO tool, originally developed by engineers at Google, which we've modified to read our custom data trace format. It processes it into a format that Clang will accept. So we save the file to disk and tell the compiler where to find it. So typically, this would be a version-controlled location so that all developers on the project can take advantage. The cost of enabling this feature should just be adding one extra flag to the release build, and then at some frequency, just updating the profile data in version control. So we tried out this on a branch based on the LLVM 3.9 release. We measured different games across various scenarios. So here's an example of the sort of results that we get from a game. So we're measuring the duration of the CPU side work per video frame rendered across a known specific scene here. Games are rarely fully deterministic, which means we can't generally compare individual frames from different runs. So to make comparison easier, let's sort these frames from shortest to longest. So now we've got a nice distribution for our frame times. So hopefully this is suitable for doing performance comparisons between different build configurations. But we're only measuring about 1,300 frames from a single run here, which isn't a very large number, and we don't know how susceptible it is to noise, so we can get an idea about the noise level by repeating the run a few more times. So in this case, we've got about 50 lines plotted on the graph, each from running the same scene from the same executable. All of the lines fit nicely within a certain area. So with a graph like this, I'm relatively confident of my noise threshold now, and we can compare different configurations. So the cluster of black lines represent a standard optimized build, and red represents a build optimized using instrumentation-based PGO data. It's lower, which on the whole means frame times are faster. So if we pick one of the black lines as a baseline, we can now subtract the value from that line at every value on the horizontal from each other line to get a nice visualization for how the results really compare. So we've switched to higher is better now, and every graph that we show from now on will be in this format. So you can see that the instrumented approach improves performance way beyond the noise threshold, about 3 to 4% by that measure. And if we apply sample-based PGO, well, it's not a total disaster. Other than a few stray outliers, the runtime improvement is clearly above the noise threshold, but it's still lagging way behind instrumented PGO. So let's at least verify our hypothesis about the overhead of collecting the data in the first place. So remember, higher is still faster. The thin black line here is exactly the same cluster of black lines that we had on the previous graph. We've just zoomed out a bit to fit the other lines in. The blue line just below is the overhead when running our PGO trace from Razer CPU Live, and the red line represents the overhead of adding the instrumentation code. Okay, let's try another game. So in this case, instrumentation-based PGO is a huge win, about 10%, 9–10% in terms of runtime performance. There are some artifacts in this data showed by the big spikes caused by the fact this game doesn't necessarily run the same amount of work in every video frame. But in general, you can see the cluster of red lines is a long way above the cluster of black lines from our baseline build. This win was not matched by a sample-based PGO. But the profile collection at least tells a consistent story. So sample-based PGO, we think, is great in terms of workflow and intrusion, but lags behind in terms of performance benefit. So I could just stop here, or we could delve in and have a look, see if we can make it better. So let's figure out what's going on. So we started by comparing optimized code produced from the various code bases when using profile guide files generated by instrumentation against profile guide files generated by sampling. And we can assume that, as we saw before, the instrumentation-based approach has perfect information with which to make optimization decisions, and the sample-based approach provides an approximation which may be imperfect. So there are a few possibilities. Either the sample data is just too poor in the first place at the instruction level, or it's not translating that data back to source level information correctly. So I'm going to hand over to Rob now, who's going to show some representative samples of the differences we found during that investigation, with a smooth microphone handover. Okay.
I've got that.
Okay.
Yep. Okay. So there's a clicker. Okay. So thanks, Greg. I skipped a bit. The first example is very simple. We have a function called myHotFunction, which is called from main in a loop with the condition set so the common function is called approximately 1,000 times more than uncommon. So let's look at this code before we apply a profile. We can see that as the compiler doesn't know any difference, it has assumed that the condition would be true, and it's laid the code out so that the fast fall-through path is the call to uncommon. But let's see what happens if we apply a profile. We get identical code. Something has gone wrong. If we look at the instruction level profile information and apply a heat map based on the number of hits per instruction, we can see that the data seems to be correct. We can see that the else block is much colder than the rest of the function. The instruction level data seems correct then. This suggests that our problem lies somewhere with the way that this data is mapped back to source level via the debug data. So let's now look at the sample after hits have been mapped to source lines using LLVM prof data. This is the profile for the function which we superimpose on the function. This number is clearly wrong. According to this, we executed line 13 as often as line 15. But the number, of course, to uncommon looks much more plausible. So there looks to be something wrong with the line mapping. Let's look at the debug locations associated with the instructions. We can see two instructions are associated with line 13. But line 15 is in the middle. Interestingly, one of the line 13s is in the cold basic block and one is in the hot basic block. Let's look at how this affects the debugging experience. So we start off in the main loop and step into the function. In this case, the condition is 1, and we step into uncommon. Step through, back to my hot function, and exit. Go around the loop again, and back into my hot function. The condition is now 0, and we step into the call site for common. Step through again, back to line 15 for the mask instruction. And then we step from line 15 onto line 13. This doesn't seem right at all. So what has happened? Well, we can see that both blocks store to P. The compiler has spotted this and has removed the identical stores from both the then and else blocks and replaced them with a single store in the successor block. But when the compiler did this, it retained the debug location of the first store. This means all hits on the instruction are mapped to line 13, which is wrong. So let's look at the code in LLVM where this commenting is occurring. We create a new store instruction here which uses the debug location from one of the common instructions, the store, which in this case was line 13. On the face of it, this makes sense. We want the optimizer to preserve debug data where possible. So what are our choices? In this case, we can attach line 13 to the instruction, so we're correct when the uncommon block is taken and incorrect when the common block is taken. We could choose instead from the other sort instruction and attach line 15, but this is still going to be incorrect some of the time when stepping. And for PGO, we don't want the hits on the common instruction to be counted to line 15 or 13. So we have two choices here, neither of which is appealing. We turn to Paul Robinson, our friendly resident dwarf committee member and debug info expert at Sony, and explained our problem to him. He told us that dwarf doesn't yet have a concept of multiple locations for a single instruction, but he pointed us at the following paragraph in the dwarf 4 standard. This describes dwarf's line of register, which is used for debug locations. The key sentence is this one. The compiler may emit the value 0 in cases where an instruction can't be mapped to any source line, such as artificially generated instructions that can't be pinned to a specific location in the source code. In our case, it's not that we can't attribute the store instruction to any source line. In fact, it's quite the opposite. In fact, we could attribute it to more than one line, but the key point is that we can't attribute it to any source line correctly 100% of the time. It is ambiguous. The reading is potentially arguable about whether this case truly fits the original intention of this instruction, but it seems a worthwhile avenue to pursue. With LLVM now able to emit line 0, we can try setting it for our new instruction. So instead of line 13, we use line 0. Let's try stepping in the debugger again. In this case, we've already been around the loop once, and stepping was correct as before. Now we've entered my hot function with a condition of 0, which is where it all went wrong before. We step into the else clause as expected, step through common, back into the else clause to apply the mask, and then straight back to the end of the function without ever hitting line 13. How has this affected the profile? Before we had this, now the hits are mapped correctly and the hits on line 13 matches the calls to uncommon. If we apply the sample now, we can also see the blocks are nicely reordered with the code basic block pushed to the end of the function. So we have our patch. It seems to be a win for both the debug stepping and for sample-based PGO accuracy. So are we all ready to commit? Well, we were, almost. But then during review, an interesting suggestion for enhancement was made. The patch as shown above works on the assumption that we can't associate multiple multiple locations with a single instruction. This is true for dwarf right now, but who's to say it won't always be the case? We don't want to lose the information with the source code that debug instructions could be merged here, so we introduced the following API. Right now, this is pretty much a stub. Unless the locations are identical, it just returns null pointer to set an empty location. If in future we are able to support representing multiple locations per instruction, this gives us a single place to do it. So our final patch now becomes this. This is not the only place in LLVM where this sort of instruction commenting occurs across basic blocks. In our analysis of differences in optimizations between instrumentation-based PGO and sample-based PGO, we found several places contributing differences that fit this pattern. So the get merged API is now used across LLVM for cases like this. So continuing our analysis of optimization decision differences, we found another category, hoisting. This example is slightly more complicated than the last one. We have a replace function that looks for characters in old that occur in stir and replaces them with the corresponding character in the new stir. Note that in the call in main, no character in old occurs in stir, so the set function should never actually be called. This is the code before we've added a profile. We can see the block with the call to set the call. We can see the call to set, is in the middle of the inner loop. As before, the heat map shows the raw samples. As we would expect, the call to set is completely cold. This is with the initial sample loaded. We can see the call to set has been moved out of the inner loop. However, this could be better, indicating there is something wrong with the profile. So as before, let's look at the hits mapped to source lines. This is wrong. This shows the line to be fairly hot, but we know it's actually never executed. Let's try to debug this code. We enter the replace function, step to the first loop, pre-header, then step to the inner loop, pre-header, but look what happens if you step now. We jump to line 16. This is clearly wrong. Let's look at the debug locations. We can now see what has happened. The address of new I is constant in the inner loop, and loop invariant code motion has moved it out of the loop into the pre-header. However, it still has line 16. This is an interesting case. We've speculatively moved code out of a basic block into a hotter basic block, but we've retained the line information from the cold basic block. In our previous example, we used line 0 to fix both the poor stepping and incorrect sample attributions. In this case, it's a bit different because we're not merging instructions or creating new ones, but simply hoisting them. It's correct that they're associated with line 16. The question is as to whether pure correctness is the most desirable thing here. Let's see what happens if we set the hoisted instruction to line 0. Let's debug it again. Step to first line, then the second loop, then the compare, which is false, and we go back around the loop. That's correct. This is the original samples. Line 16 now becomes 0 as expected. Finally, this is the code using the new sample. It's too big to fit on the screen, but you can see the ret. Which shows the cold code has been moved completely outside of the loops. But what's nice is that all of the spills and reloads across the call to set, which were previously scattered across the function in hotter basic blocks, have now all been moved into a completely cold basic block, leaving the loop completely spill free. Sacrificing the line information for the speculatively hoisted instructions seems to have led to better debugging experience and more accurate PGO data at the expense of pure correctness. We suspect that in the longer term there may be a better fix, such as using dwarf is statement flag to specify recommended breakpoint locations. We need to ensure that LLVM is consistently setting the flag, and also all consumers, such as debuggers and auto FDO, respect the flag. So this is the last example. It involves vector constants. In the function, we have a vector constant where the first use is within an if. The second use then occurs after a call to a function. Note the if condition is always false, so line 15 is never executed. Let's see what we get when we profile this. We can see that a function profile is about the same for all lines, and line 15 is hot, which is clearly wrong. What happens if we debug this? We start on line 11, step to 14. If we step again, we go to line 15. But the condition is false. We then step to the call, enter do something, and back to hot function, but we jump to line 15 again. The condition is still false. We then step to line 17 for the sub, and back to main. The odd debugging is caused by two problems with the debug locations. First, there's no debug location for the push instruction. This means it gets line 15. The second problem is the location of the vector load. The register allocator has rematerialized the vector constant after the call. However, it has a debug location from the first use. Fix is to use line 0 for the push. Vector constant gets the location of its use, which is line 17. Let's debug it again. Step to line 14. Stepping again goes to 17, which is correct. And to do something, and we return to hot function line 17, which is correct. This was the sample we got before. After the fix, the line now gets 0 hits. At this point, I hand back to Greg again to wrap up.
Cool, thanks, Rob. Okay, so these three examples represent some of the main categories of debug location issues that we found introduced by optimization. But within each of these categories, there were actually a number of things that fit them that we've made fixes for. So the good news is that our worries that we'd have to deal with cases where the debug data we needed for good debugging and for good optimization being different are not founded. In fact, it's quite the opposite. By improving one, we seem to be also improving the other. So there are still a lot of differences left, but let's see how the results compare currently. So this is how we were before. Blue line is above the black line, so Sample-based PGO is better, but not as good as instrumented. And with our debug data fixes applied to that branch, this is where we are now. So we're still behind, but we know there are still issues remaining, so that's to be expected. With the other game, here are the original results. Sample-based PGO is again an improvement, but nowhere near the benefit of instrumentation-based. And our current results show that we're now way closer. So to summarize, we believe that sample-based PGO is now a viable alternative to the instrumentation-based approach for our target. It's easier to initially set up, as it doesn't require separate build configurations for collecting and then using the profile data, hopefully requiring much less time investment from our users, and profiles can just be collected with the click of a few buttons. As we saw earlier, it has significantly reduced runtime intrusion compared to the instrumented approach when collecting the data. Instrumentation-based PGO is still providing the best final performance benefit. So we plan to continue providing both technologies to our users, even if the sample-based approach has the effect of convincing users who would never have even tried PGO to give it a go, and then if they're suitably impressed enough to try instrumented PGO for the final performance benefit that it gives above, then we still consider that a clear win over the possibility they wouldn't have tried it at all. The additional huge benefit is that the optimized debugging experience is also far nicer now than it was before, we found. We still think we can improve the performance of the sample-based approach, and we're hoping to close that gap as far as we possibly can. So one other just interesting side note we noticed, by measuring the performance difference between a baseline build and a sample build, we can actually spot cases where the debugging experience has gotten worse just by seeing that the improvement is not as good as it was. So it's not a perfect measure, clearly, of the optimized step in quality, but it's interesting and potentially useful. So I'll just end with a quick summary of the advice we've come up with while investigating and improving these issues. So when implementing new optimizations, new transformations, please consider the impact on debug locations. Although instinctively it seems that the optimizer should always try to preserve locations, we found that when multiple basic blocks are involved, it doesn't always lead to the best debug experience or sample-based PGO data. If you're commenting instructions, use the get merged location API. So we plan to continue working in this area. The technology is still relatively young, so we're really excited to see where we can all take it together. Thanks everybody for your time, and if anybody has any questions, we'll be happy to try and answer them.
you use debug info and more specifically source file mapping for profiling, and we explained that all the changes that raise debug info you did in this mode, specifically question. So when you use debugging for, not for profiling, for actual debugging of optimized code. So you have the options. First, retain debug info, and sometimes you get, as you demonstrated, some strange behavior in the debugger. Second option, remove debug info. But in this case, for example, if your code has some function code, the user loses ability to say step into this function if you remove debug info from the code side of this function completely. So now final question. Sorry for being so long. Do you have experience with your users debugging optimized code? Did you face this problem at all? And if yes, so what you found way to prefer? Have less debug info but more logical debug experience in debugger, or more debug info but sometimes logical experience?
So it's always a trade-off. And it's kind of analogous in some ways to displaying the values of variables in the debugger as well. So kind of the question is it better when you're not sure to display a potentially incorrect value, or is it better to just not display anything at all? And the answer that we've always get from our users is they'd rather nothing at all than see something potentially wrong. So we think it's the same for line stepping in the same way. It's not ideal. We're kind of stuck with, we're trying to represent something in a format that can't perfectly represent it. So there's always trade-offs to be made.
Thanks.
Do you want to add something?
I'd also like to add that we actually would never remove the debug information associated with the core instruction.
Good point.
Okay, any other questions?
You mentioned that there would be no clash between the goals of the debugging experience and what the usage of profiling. Again, expected the example of the hoisting was another some thinking. If that's a load into a store and an access is an invalid non-assigned memory indication, you get a segmentation for it. Usually you would get source line location of it. But in that case, if you set it to null, you don't get the source location of it because it has been hoisted. But for that one, I would want the source code location. So maybe we may have to switch between two modes of what I want also.
Well, as far as I'm aware, the compiler will not speculatively hoist instructions which could cause the program to cause an error. In this case, the instruction that was speculatively hoisted was get element pointer, which is perfectly fine to speculate. It will never cause a failure.
But if excesses are undefined behavior, the compiler does hoist that.
I don't really know how to answer that.
So yeah, I mean, it's a similar answer to before. From me, it's always a trade-off. And so we've made the decisions that we feel are best for our users. But again, our users have very low expectations for the optimized debugging experience. And so the feedback always is that we meet the low expectations. And so they're used to stepping into the disassembly and figuring out what's happening at that level. So certainly from the point of view of our users, I don't think that would be an issue, but maybe I can understand the point now. So.
So have you actually seen some cases where it's often better to keep incorrect information? And if yes, do you suggest to have some configurable strategy for making this decision?
Do you have an answer for that one?
It sounds rather lame answer, but as yet, we haven't really seen any case where actually what we want to do for SPGO was actually bad for debugging.
Maybe just a comment. Like, as is shown, we basically removed our allocation of store when we were grouping those scopes. And suppose someone is just stepping in assembly on that instruction. He just wants to know where that assembly instruction came from. Now it doesn't have any idea from which place of the function can potentially come. Okay, it was wrong, it was shown only from one place, but at least it was giving some idea. And smart users can guess what Kamar can do as well. So that's what we see in embedded sometimes, the opposite way. So that's why I'm asking whether there should be some strategy for one of the use cases potentially.
Well, okay, I've just remembered a case where it doesn't affect us, but for SPGO, but it does affect generally LLVM, is that the address sanitizers, the sanitizers tend to use debug information to associate stores, etc., and stuff like this does lose the association. There's no easy answer. There's been a large debate on the forums about this, and generally the movement is towards maybe having some sort of different mode, yes, but it's not something which people want. It's only really if there's no other way. Because obviously we don't really want people to have to be using different configuration options, because for SPGO, one of their main workflow benefits is that they just use existing builds.
Yeah, so as kind of Rob touched on a bit earlier, that there is a potential way forward to use, Dwarf has this concept of is statement. And at the moment, the heuristic in LLVM is basically, so is statement basically tells a debugger kind of a recommended place to stop when you step. And right now, the heuristic is pretty much, if the line is different to the previous line, then set is statement to 1. So probably we could get away with smarter heuristics in that teach all of the consumers, like AutoFDO, to understand what that means. And then we could preserve the line information, but also preserve the benefits that we've kind of got from this approach. But that's not an insignificant piece of work.
Okay, if there are no further questions, let's thank the speaker again.